Our research problem is to define cage-based coordinates allowing non-rigid deformations while enforcing as volume-preserving as possible properties. Key to our work is a novel fluid-inspired computation applied to cages. We introduce a novel deforming weighting scheme by considering a compact stencil for approximating Stokes equations. Recent years have seen a demand for physics-inspired character. Moreover, quasi-conformal coordinates are an important feature for cage-based deformation. Our work differs from previous works in the sense that we use flow dynamics for computing cage-based coordinates and not in the traditional context. Also, we take benefit of the harmonicity of fluid dynamics for manifolds. Cage-based deformation is of great interest to recreate non-isometric deformations. To the best of our knowledge, our work is the first to devise a cage-based coordinate system starting from the incompressible Stokes equation as a model for weights computation. Our contribution is a mathematical link between Stokes fluid mechanisms and the cage-based problem. We reformulate cage-based rigging into an amendable incompressible Stokes problem with two phases: Stokes linearization and biharmonization. We derive a compact Stokes approximation using a one-time cell neighborhood stencil. We use a volumetric solver to perform iterative weights conduction. First, we start from the incompressible Stokes equation. Then, we linearize the Stokes coordinates. In the third step, we derive a Stokes-based biharmonic form, expressed with a compact stencil. Finally, we use an iterative volumetric solver to obtain our Stokes coordinates. For instance, using our Stokes coordinates, the default pose of the armadillo model is deformed in space-based fashion using a collection of target cages. We assume the basic assumption of having an incompressible creeping Newtonian flow with constant density and constant viscosity. We derive the so-called stream function with linear form for the Stokes flow by neglecting the unsteady convective terms and nonlinear advection term. We restrict it to zero pressure. The Navier-Stokes equations are reduced to which is the biharmonic limit, also known as Stokes flow. The Stokes-based biharmonic equation is a fourth-order partial differential equation. We compute our Stokes coordinates using a volumetric solver. The cage is voxelized, and the boundary condition is set up. We show a cutaway slice of the voxelized cage interior during propagation. The close-up view shows the visualization of the fluid weights propagation from a given cage handle. At the steady state, Stokes coordinates are obtained for each model vertex by trilinear interpolation of the grid cell values. This biharmonic formulation of the Stokes equation is discretized using centered differences in the 3D space. To greatly simplify boundaries management, the compact stencil is limited to one-ring compact cell. Our framework offers three cage-based applications: interactive mesh editing, shape encoding, and performance capture reuse. A default pose of the ogre model is encoded into cage-based shape using our Stokes coordinates at a low distortion rate. Taking as input the default pose of the horse model and its cages, we produce as output a sequence of stretched cage-based shapes. The default model is surrounded by a shape-aware coarse cage. The reference model poses are encoded with our Stokes coordinates. We visualize the resulting distortion injected by cage encoding for the camel and flamingo model. Using with our Stokes coordinates, we establish statistics for a various collection of cage-based organic shapes. The low-rate distortion leads to visually pleasant deformed shapes. We compare mean value coordinates and our Stokes coordinates. Our coordinates finally encode the lips and jaws of the horse with quasi-conformality properties. We reuse highly detailed performance capture meshes by decomposing the template shape into a collection of cage handles. Coupled with our Stokes coordinates, the template mesh is locally squashed and stretched, satisfying as volume-preserving as possible non-isometric deformation. Our compact Stokes coordinates are reused for space-based deformation of several deformed poses. Our efficient formulation allows us to deform a given enclosed object with a collection of deformed cages. The deformation is simply achieved by displacing the location of cage handles with low distortion rate. We introduced Stokes Coordinates as a new higher-order coordinate system for cages with non-isometric properties. We demonstrate a proof-of-concept Stokes solver for rigging application, taking benefit from a linearization and harmonization formulation. Reduced to their biharmonic form, Stokes flows serves as cage weighting functions. Finally, we show that the Stokes coordinates can be discretized using a one-ring grid cell stencil. Thank you for your attention.
You caged me in your home like I was something you own. Well, what did you expect? You caged me